It's my pleasure to announce a lecture by Marek Filakovský from Institute for Science and Technology in Vienna. This is a joint work with Lukáš Vokrinek, and he will talk about complexity of computing homotopy classes. Marek, please.
Thank you very much. I would also like to thank the organizers for organizing this nice meeting or conference. I think I have the longest title, but I hope this is not the longest talk. So everything I'm going to be talking about is contained in this paper, which appeared on Archive recently. It's a joint work with Lukáš. It's called Computing Homotopy Classes for Diagrams. And I'm going to go what this diagrams really means at the end of this talk. But for now, let's concentrate on the two main results. Let's start with homotopy classes of equivariant maps. Okay, so for simplicity, assume somebody gives you simplicial complexes, X and Y, and there's an action of a finite group G on these finite simplicial complexes. Well, this theorem says that under some stability conditions, basically saying that dimension of every fixed point for every subgroup of G is less than twice the connectivity of the fixed point on the target, then there is an algorithm which computes the set. Well, the set will turn out to be some nice algebraic structure and a set of all equivariant homotopy classes of maps. And when you assume that you have some sub-complex A of X, then you can talk about homotopy classes of maps extending something already given. Okay, and what is interesting is if the dimension of X is fixed, the algorithm is actually a polynomial-time algorithm, right? And an important remark is if the stability condition, the dimension connectivity and that connectivity for each fixed point is greater than 1, if this condition is not satisfied, that the problem is algorithmically undecidable, actually. So on the right-hand side for this greater than 1, this follows from word problem, essentially. And on the left-hand side, this follows from Hilbert's 10th problem. Okay, and regarding this conference and what most people know is basically corollary of the previous result, saying that the Tverberg problem is polynomial-time decidable in this range of dimensions. Basically, it's just in the metastable range. Okay, so let's go to Tverberg problem because that's what people, I guess, know about. Well, definitely, I know the least of, and you guys know the most of. So this is the R almost emitting problem from the previous talk, in my case. So I'm given a finite simplicial complex K, and I'm asking for a piecewise linear map to RD without R tuple intersection points between pairwise disjoint faces. Okay, so in the special case where R is equal to 2, this is precisely the almost embedding problem, right? So I think from the previous talk, this is precisely the R almost embedding. Right, so for me, I call it Tverberg. So I think both of them, actually, in this case, both of these should be R almost embeddable, these two simplicial complexes. Yeah, in the first case, imagine we're projecting onto a line here, and I guess I can project all of this into a point, and all of this into a point, right? And then kind of linearly extend, and that should work. I guess the other one is also possible. Well, anyways, if we formally write it down, then we have a problem of this type, which has these parameters R, K, D, and in this input, where K is finite simplicial complex of some dimension, I'm asking, can I decide whether the R almost embedding exists or doesn't, right? I just want to point out that I'm not actually constructing this almost embedding. I'm just saying it is or it isn't there, right? So kind of in general, when we look at this type of problem, when D is very small and K is very big, this problem is going to be impossible, right? You're not going to find this map. This is just an observation, basically, by the dimensions. On the other hand, if dimension D is big, you will, in the end, find some R almost embedding. So the question is really what happens in between, and what our result says. Okay, in this range, which is called the metastable range of dimensions, this problem is polynomial-time decidable. Okay, so this fixes it here, and there's a question what happens in this remaining part. right? So for r equals 2, there are many results regarding this area. Well, for us, we just said something about the blue one. Okay, so what is interesting about this metastable range? So we can do the same thing which people use in r equals 2, which we can use the deleted product. So when we have this r Tverberg map, which is this r almost embedding, then we definitely can induce a continuous equivariant map. So this is the symmetry group X. So this is like r-fold deleted product. So we take r-fold product and remove the fat diagonal, and the same we do for the RD. So you obtain a equivariant map like this. And I just want to remark that the action of this group is now free on this fat diagonal and not free on the sphere. Okay. And what we really utilize is this result by Mabillard and Wagner, which tells me actually the opposite in this metastable range of dimensions also appears. So if there is this map and we're in this range of dimensions, there is an R-Tverberg map. Right, so this is generalization. I see it as a generalization of the Heffliger-Weber theorem, essentially, right? But basically, we had a question about existence of a map from a simplicial complex to RD with some properties, and this is a question about existence of equivariant maps, right? And that's basically question of this form. At least I can write it like that in homotopy theory, right? So I can have a set of equivariant maps from this deleted product essentially to the sphere where there's an action of the symmetry group. Question is, can I decide it? And ultimately, you know, at the beginning we saw that if some stability condition holds for fixed points, then we can. And this is precisely the answer, right? Just checking these dimension connectivity conditions, and it turns out that yes, it is decidable. So from now on, I'm not going to be talking about the R-Tverberg problem anymore. And I'm going to move on to homotopy theory and these computations in homotopy theory, which is basically what we do, right? We compute this set of equivalent homotopy classes of maps, right? So in general, what people do is compute invariants, right? So you have homology type of invariants, you have homology, cohomology. Sorry, back. Can we go back one slide? Right, so these are, I would say, easy. Of course, depending what you want to do. If you want to compute this homology of a simplicial complex really fast, I guess it's not that easy. But you know, conceptually, someone gives you a simplicial complex, you should be able to compute homology and cohomology. But with homotopy, you know, say you want to compute homotopy groups. You want to compute pi of x, that's harder. Now here I've given it in the more kind of the most complex conditions where we do it relatively to some, so we fix the map on some subcomplex of x here, and there's a fixed map to A, and we also do it over some fixed map to B, and this is called the lifting extension problem. And finally, you can ask, okay, are two maps homotopic? Or indeed, another type of question like this is if x and y are homotopy equivalent. So these are, I would say, wide, hard questions and haven't been really in the mainstream of algebraic topology that much. That's why you don't really hear about them, but some things are known about this, okay? So let's move on. So let's go through the past results in this area in general. So in the 1950s already, there's a result by Brown, and he presented an algorithm. There was basically no complexity, right? Bad complexity, I would say. And he had additional condition that these homotopy groups of Y are finite. He had a special case where Y were spheres. It should be reminded. Then this is already, this should be in 20, oh, can I really erase this one? And this was, I think, in 2012. So there's an algorithm which computes the set using kind of modern approach, which we are also using, and in polynomial time already. And this was further generalized by Chade-Krčál, and so these are Chade-Krčál, Matušek, Vokřinek, Wagner. And we should also list Francis Sergerat, who had important contributions to the way this is computed. And he is mentioned in the end in the acknowledgement. Then in Chade-Krčál, Vokřinek, which there's a version on arXiv already in 2014, I believe. They present an algorithm which computes this set. So actually this hard is this lifting extension type problem. And also there's a free action. So if there's a finite group G which acts freely on X and Y, A and B as well, then they present an algorithm which computes this. Then there's a joint result with me, myself and Lukáš. We had an algorithm which computes this set and decides whether two maps are homotopic. And this only wants that connectivity of Y is greater than 1, by the way. Everything else wants this dimension connectivity condition, but this one doesn't. That's because of this suspension somehow mysteriously helps us there. And finally, our result, this most recent one, which we compute this set where G is a finite group. Okay. Clear our drawings, and let's move on. All right, so what are the main steps that are used throughout all of these papers? I'm going to talk mainly about the simplest possible case when there's no action on the group, and I'm going to return to this group action at the very end. But kind of the main ideas are, first of all, approximate your target space Y. Okay, you may ask, why would that be a good idea? But it sort of makes sense, right? So say already your X looks like this. X is a triangle, and Y is some larger cycle, right? And already kind of representing a map X to Y, which induces something non-trivial on this first homotopy group, right? Say like 3, like this one's, we want this circle to look 3 times along Y, right? But how do you represent it in some kind of nice and simple way, right? You need to subdivide X quite a lot of times, but subdividing it creates like a huge representation in the computer. So we do it somehow differently. We use the language of simplicial sets. So now everything is a simplicial set. And these Postnikov stages has this nice property. They are so-called fibrant. Okay, this word will come up later as well, but for now this is all. It's need to be moved. Okay, so that was the next step. So why do I construct this tower? Another interesting thing is when the dimension of X is finite and X is finite simplicial complex in the beginning, then I have this isomorphism. So really, I don't need to compute the classes of maps from X to Y. I need to compute from X to this approximation. That's fine. And next, the stability assumption, this dimension connectivity assumption, gives me that this set really has a structure of an abelian group, which is important because I need to compute this set somehow, right? This is normally a set, but in this case, this is an abelian group, so I can compute the generator, so represent the generator somehow. This is really what we mean by computing this set. And another thing, because I have this sequence of approximations of my space Y, there's a difference between these approximations, and this difference can be captured, right? This can be computed, and this helps me kind of inductively, step by step, compute the set XY, which we want. Okay, and also another important tool is we somehow need to represent these mathematical objects, these stages, in a computer. So in a moment ago, I said, okay, I don't want to do some infinite subdivisions, that's bad. And now I'm saying I have infinite objects, and somehow I'm claiming this is much better. But somehow these mathematical objects, although infinite, can be better handled than these infinite subdivisions. Okay. So let's go into a bit more details about these Postnikov towers. So what it is, the sequence of approximations. So basically the nth stage, and your space Y, have the same homotopy groups until the dimension n. Okay, and the higher homotopy groups of your Cosneco stage are 0. Right, so this is like having the same homotopy up till the dimension n-1. This has the same homotopy up till dimension n. Now, how do I construct the other space from the dimension n-1 to dimension n? Okay, I have this Eilenberg-MacLane space. So Eilenberg-MacLane space has this property that it has all information. So all information is in this dimension, you know, all homotopy information, and this is the only non-trivial homotopy group there. Right, so you kind of glue on this non-trivial homotopy group onto everything else, and you need to do it in some nice way, such that this map really is inducing the isomorphism on these homotopy groups. But this can be all done, and this is well known that you can do it in algebraic topology. The question is how to do it kind of in an algorithmic way. How do I represent everything? Okay, so the theorem, which appears as the first step of the construction, is really when I have simply connected, one connected simplicial complex, then I have an algorithm, a polynomial time algorithm, which computes this Cosneco tower and somehow finds this object. I said this object is infinite, so I need some nice representation of this object, and we'll get to that. So the other step is this difference between Cosneco stages, right? So I said they differ by the nth homotopy, which is indeed the case. And this map is actually a fibration. So you can capture this by a fiber. You can think about it as fiber bundle as well, actually. So you have this fibration, which induces a long exact sequence. And this long exact sequence looks like this. This is just simply rewriting everything in the form of this long exact sequence. And using this fact that maps from your space X to your Eilenberg-MacLane space are isomorphic to computing kth cohomology of your space. This means that we're in this setting, and from this long exact sequence, I can cut out this short exact sequence. So kind of inductively, if I want to, and I'm not going to be precise again, because I just want to give out the idea, but somehow, if you want to use some inductive reasoning, right? So you are able to compute this by induction, okay? You are always able to compute this in some meaningful sense. This is some group. This is cohomology group with coefficients, and here it's fine. You can do it. Same here. Now here, this is a bit tricky, but essentially the point is the target is this n-1. So, okay, you can compute it as well. And everything is a abelian group, or close enough to be a abelian group. So you have a sequence of groups from which you can cut out the short exact sequence, because, you know, you just find out all the images of alpha here, and you factor it, and here you take the kernel. Well, then you find a section, and you compute yourself the structure here. Well, that's the idea. That's how it's done. So you need to do it all algorithmically. So let's talk about what it means to do things algorithmically. So we have this infinite object, infinite simplicial complex. Actually, it's simplicial set, but let's think it's a simplicial complex. So I have something infinite. So how can I compute with it? Well, you can approach it kind of locally. That's the first idea, right? So somebody gives you a bunch of bits, data D, and I have an algorithm which tells me, oh, this data is actually a simplex of a simplicial set, and I'm happy with it. And I ask you, okay, given this is a simplex, given it is a simplex, can you give me some kth phase of this simplex? And it runs and outputs me a different string of data and tells me, yeah, this is a phase. And yeah, that's me. That's cool, and I can live with such a structure, right? Nominally, it's just a collection of algorithms, so I have them in the computer. Now, this is local definition. If I want to have a full definition, I would need to be able to basically output all n simplices. But if this is infinite, then, you know, I will never stop. So it's probably not the best. So I need some kind of, I still need a way of managing these infinite spaces in this formal way. Now, let's think about abelian groups, though, what it means to be like a local abelian group. Well, there's an algorithm which gives me the representative of the neutral element. And whenever something is representing elements A and B, I have an algorithm which outputs me their sum, and I have an inverse. So that's very local, and what I call something like a fully effective or effective abelian group, so a full expression, is basically somebody outputs you the isomorphism type of your group, right? So gives you representatives, concrete data, and okay, this represents this group as such a complete description, right? So this is a fully effective structure. This is, in a sense, finite, whereas the first one is infinite, right? So the same for chain complexes. So we have a possibly infinite simplicial set or simplicial complex, but we still want to compute with a chain complex. So how is this done? So the chain complex is called effective if, you know, at every n, this is a fully effective thing and all the maps are computable. But something is homologically effective if this set is possibly infinite, but there is a reduction or strong equivalence, or chain homotopy equivalence from the chain complex of this X to something basically finite, right? So I can reduce this huge chain complex to a small chain complex with which I can simply compute with. And that's all that's necessary for me to actually work with these spaces. So all of these Eilenberg-MacLean spaces, all of these Cosneco stages are homologically effective. And if you want to be very precise, you can actually say, okay, all the results are for homologically effective simplicial complexes. I didn't need them to be finite in the first place, but you know, that would be a bit too much, I guess. So this is how it's done in the very the simplest case with no group action. So now what is happening when there is a group acting on it? Okay, so first of all, we can introduce this category of orbits whenever we have a group. So let's say I have a Z2, right? And I have a category of orbits. So this category of orbits has the orbits as an elements. And what are the elements? One is Z2 over Z2. One is the Z2 over the trivial group. And I'm going to get the map like this. And there's going to further be a map like this in this case for this group. So this is the orbit category for G is Z2. And what is interesting is whenever I have a space, it doesn't have to be simplicial set, but when I have a space with G action, I can kind of map it into this category of orbits. So the category of orbits has a lot of elements, and for each subgroup H, essentially, or for each orbit, the element is the fixed points. So in this case, I hope I didn't make a mistake before. So for my simplicial, if I have a simplicial complex with an action of Z2, this looks like something which is fixed by nothing and something which is fixed by the entire group. So these are really the fixed point. This is not fixed point. This is the entire space. And is expected I will have a map which will be an inclusion, right? Because these are the fixed points. And here I have the map, which is the action of the group. So no information is definitely lost by doing this, right? And somehow a classic result from equivariant algebraic topology is the Elmendorf's theorem, which tells me, actually, if you want to compute the equivariant maps up to equivariant homotopy, you can do it in this category of diagrams. So say, move everything to these diagrams, compute there. And this is exactly what we do. So we compute in this category of diagrams. We don't have single spaces, but we have collections of spaces with maps between them. So that's the novelty of our approach with Lukáš. Okay, let me maybe erase this. Right. So I said in the beginning that the paper is called Computing Homotopic Classes for Diagrams. So maybe the observant people already see where the diagrams come. So our main theorem in that paper actually reads like this. So our objects are like finite diagrams. Finite diagram means there's a category with finitely many objects and finitely many arrows, such as these orbits. But we want to work even more generally because we're mathematicians and we somehow want to be as general as possible in a given setting. So this A we can ignore. This is just the relative statement. And we say, okay, under some dimension connectivity condition again, then we can compute this set of classes of maps between diagrams, and given the dimension is fixed, the algorithm runs in polynomial time. Okay, again, how do we do it? Okay, there's some mention about, okay, let's ignore this for a moment. So how do we do it? We basically generalize everything and try to overcome whatever obstacle comes our way. So we need to generalize the representations, but this is somehow fine, right? We already had a representation for the objects kind of pointwise. So we just have multiple objects and map between them. Right? We can deal with this. Then we need to construct the Cosneco tower for these diagrams, okay? And then we need the exact sequence. So this is all there is. So how do we deal with it? Okay, so somehow there's a complication where there wasn't before. So in simplicial sets, and I don't know how much you know it, but basically for CW complexes, everything is both fibrant and co-fibrant. And in diagrams, it's not the case. So co-fibrant, I will call it cellular. So I have let me maybe go like this. So say I have a diagram like this. There's an object x0, x1. It's just two objects and an arrow, right? And let's say this is a point and this is something, I don't know, sphere. Right, I have a map like this. So this diagram is not co-fibrant, because for it to be co-fibrant, I would need the cell here to be mapped to a cell here. Kind of, it's sort of injective. Injective is not the right word, but as this cellular statement says, okay, cellular is basically co-fibrant in this setting. I mean, I have a collection of kind of generating simplices. So for every simplex, I can get it uniquely from a cell somewhere in the diagram as an image of this of maps. And for this point, it doesn't hold because this point is an image of everything. There's not a unique pre-image of this point, and that's a problem, right? So by the way, these fixed points which we had before, these are all cellular co-fibrant. That's okay. That works there. Okay, we have the same setting for chain complexes, right? So it's effective if it's cellular in a sense. We need it for computations, computing the homology groups and the right relationship between them. And from homology groups, we compute homotopy groups. So this hidden machinery needs these properties somehow. Okay, so when we compute this Cosneco tower, we really want these stages to be co-fibrant, to have this cellular property, because only in that case does this map kind of represent the right homotopy class. This is a theoretical necessity for us to do this computation right. And the problem here is whenever we let's say this is indeed co-fibrant and we have a map to this, that's fine. We can do the pullback, but now this fails to be co-fibrant, so we need to repair it somehow. Okay, so we do repair it. We do repair it by computing the co-fibrant replacement. And now I guess you will be confused, but I actually already know what a co-fibrant replacement is. So say we had this case as before, when we had S2 and a point. And what we really end up with, you take a mapping cylinder. So in the simplest case, you take a mapping cylinder of F and S2, which now is nicely included in this mapping cylinder. And this now is co-fibrant. And you can generalize this construction to these finite diagrams, right? That's all I'm going to say. You can work with these co-fibrant replacements. That's fine. So I have this space. which was wrong, but now I can replace it with something cofibrant, which is really nice. That's good, but now there is no map here. So I can only overcome it by making cofibrant replacement of my tiger space as well. This, by the way, means because I had map of here to here, I need to have a cofibrant replacement here to here. So it complicates stuff a lot, but we can overcome it, right? We have a means of dealing with infinite spaces. We can overcome everything. So even though the tower now looks like n-fold replacements, that's fine. We had again a log exact sequence. The sequence is a bit more complex than before, and I'm hiding a lot of things away. But essentially, it still works sort of as intended, right? Still, from this long exact sequence, I can get some short exact sequence. And from the induction hypothesis that I can compute the map here. This is a cohomology group. This is also a cohomology group. This is computable, right? So I can compute the data here. I can give this the structure of this fully effective abelian group, or whatever is necessary for me. That's how we do it. So in summary of like the entire construction, so what we actually do is we compute a set of maps between some diagrams. In our case, it's diagrams of some in some orbit category. Well, this computes the set, and this implies the solution to the Tverberg problem. Okay, and I think I'm done. So here are some references apart from the paper which I mentioned in the beginning. I hope this gives you some kind of rough overview. So from here you can jump into these papers and have a good idea kind of what's going on. I think actually the second paper is a good starting point, because the introduction was co-written by Matuszek, and he gives these really nice introductions. And I also should mention that Francis Sergerar created a lot of this machinery of computing this effective homology, this homology for infinite objects, and so he has this kind of thing. So if you want to check some computations like that. Okay, thank you.
Well, let's thank the speaker. The old-fashioned way. Yeah, that's good to hear that. So, any questions, remarks, comments? I will see if someone raises a hand, but you can just feel free to ask question directly.
Let me ask a question. Marek, you mentioned Mabillard-Wagner metastable dimension deleted product criterion. Are you able to recover gaps in that proof by Mabillard and Wagner?
Well, okay, I'm not that super familiar with it. To me, we wrote a very nice paper about equivariant homotopic classes of maps, and I'm not aware about gaps in other papers. To me, if there's a paper and I have an application, I mean, okay, listen, I don't know about that, but definitely, so kind of, I was looking for applications of this setup to generic problems in equivariant, like equivariant problems, right? If there is a computational problem in, say computational topology, and it poses a question about the existence of equivariant maps, that's inherently interesting to me. So that's how I utilize this, right? I'm not aware of any gaps or no gaps. I don't want to.
They are present. They are publicly available for years.
Okay.
Actually, a recommendation. I don't mind my name not being mentioned there, but I think a paper containing a complete proof should be mentioned.
So Arkady, then please, I really am not very familiar with this, so but if you can forward me or send me an email with this, I will definitely check it out. I mean, we sent this paper joined with Lukáš to some review, so I would happily update it such that it's all fine.
Yeah, I'm sending you a reference in chat.
Thank you very much.
And any other question? I have a quick one.
Okay.
So, well, several, but I'll ask the most geometric one.
Okay.
What is the status of the embeddability of two complexes in R4? Is it decidable? Because there is an old result about it is 3 SAT complete or something like that, but is it decidable? Yeah.
Oh my. Pavel, do you know? Pavel
So you are given
the
finite simplistic, finite, let's say two-dimensional simplistic complex, and ask.
The status is unknown so far.
Unknown, yeah.
It's
it was like it was
right?
before.
That's all we know.
Because it's nice, it's so beautiful problem. It is just a 4-dimensional analog of the planarity, and yeah, it's nice to know that it is unknown.
There's plenty of results, even in this like R equals 2, where it's unknown. So
I see. Any other question? Because we still have a few minutes for discussion.
Let me strike a personal note. I'm very happy that we have 2 participants from Czech Republic, in spite of complicated relations between our countries. And I hope that this is our small contribution to peace efforts.
Well, let's have an applause for this. Yeah, thank you, Arkady. That's very nice to say. What about Rubio and Sergera? So how do they interact with them? Because Sergera has for many years has this program of developing algebraic topology in a computable way. How far? Of course, there are different interpretations, and sometimes even if you prove decidability, it is very far from effective calculations. Arkady said, can you really apply it? As we know, algebraic topology calculations can be very complicated, and even though it is in principle possible or computable, yeah. So, but Sergera used the computers heavily. So
yes.
Do you know what would be an update on? Do you have any insight?
So
using it in actual computations,
he
would compute homotopic groups of spheres and things like that.
Yeah, sure. So we had some sample computation. So the result is theoretically very nice, like it's polynomial time in fixed n, but it still means that the computation takes an unruly amount of time, and basically it's only sensible to compute between something of dimension. Like I don't think we ever compute anything beside dimension 6, theoretically 10, right? What Francis Sergera does, he has implementation in some kind of like functional programming way. So in theory, there's a full implementation, but the effectiveness of this implementation is very questionable, let's say, right? And I actually wanted with Lukáš, I don't know, Lukáš asked for some grant money, so let's see how it pans out. But I would really like to see actually like an effective implementation, because I think that Sergera at the company, I mean, they are very interested in actual implementations, but I don't think this is such a big thing for them. I don't think they care about it that much, honestly, in this like theoretical homotopy thing. So I would like to work on it a bit more, or just ask some computer scientists, because there's a lot of nuances in computing Smith normal form very fast, right? There's this computation of kernels and co-kernels of abelian groups, and it really boils down to doing it. And there's a lot of questions, even for algebraic topologies, like low-dimensional questions about the homotopic groups or these relative homotopic groups, and they are really tough, and people do it by hand, by some approach, even though theoretically you can compute it using something like this. So yeah, there's not that much concrete to be computed. It's unfortunate.
We still have a little time, because Pavel is supposed to speak in 6 minutes. So is there any other question or remark? Well, then we can postpone it for some other occasion. We continue in 5 minutes approximately, if you agree. And let's thank the speaker one more time.
Thank you. Thank you very much.